I think it's sort of being ignored by the community. And that's my comment. I also have a comment to Roberta, but maybe we can deal with that afterwards.
Well, if you want me to...
yeah, please feel free to answer.
Well, my primary concern is that we've gone through all this when the standard model was being introduced. People also had the same difficulties before we understood how to renormalize the theory properly. It is also asked, can we do something about those signs in the propagators? It was realized there were difficulties, just like we have in gravity now. We used to have the same difficulties in standard model in the Stone Age, so to speak. And the answer turned out to be do it right. Look exactly at the Feynman rules, try to construct in such a way that all these false signs do not occur. That was the only correct answer. And that turned out to be possible in a beautiful way. So that, and that made the standard model work. And indeed, it was found that nature takes good care of this, that indeed all degrees of freedom of nature are such that the signs come out correct. And we don't have to fiddle around with or cheat somehow to get things look right after all. So that turned out to be the correct answer. Now I'm very worried when people in gravity say, and now we don't know how to do it anymore. So let's drop those requirements and let's go around poles with the wrong sign and so on. It doesn't look right to me. For instance, and I saw that Richard Woodard was asking this question, what are the primary degrees of freedom of nature? So think of all these fields that we introduce as primary fields in gravity, as fields which are degrees of freedom on their own, and then ask, what's the most general field configuration you can allow for, and how does that propagate in time? And of course, it propagates in time using quantum mechanics, but nevertheless, that also is a propagation. So like in any theory, be it quantum mechanical or classical, you have to say what the degrees of freedom are and how they evolve in time. And when there's lack of causality, we have a problem. And the problem is much more severe than saying, oh, well, let's allow for a little bit of cheating here and there, and we'll get away with it. I don't believe so. I think we can only get away with a complete theory that has all the signs taken care of in a proper manner. And as I showed in my lecture, when you have when you have this wrong metric particle, it means it has negative metric, so that it subtracts rather than adds to the number of degrees of freedom that you allow in our intermediate states. And I was thinking, that's an interesting idea. That doesn't have to be wrong. It may mean that some two graviton states simply are not degrees of freedom of nature. They have to be removed from the picture rather than added to the picture. Removing things is much harder than adding things. So we have to go through that procedure, I think. But in this talk by John Donegal, it was argued that maybe you can get around it. I have some doubts there because then I don't understand anymore what I'm doing. And our perturbation theory is not a theory by itself. It's a theory based on some ideas of the primary degrees of freedom. So let's try to get those right first and then do perturbation theory. That's my general answer to questions of this sort.
Maybe John, you want to say something?
So maybe I'll make some comments. I don't know. In some ways, let me first return to Richard's question about the classical limit. One of the things I could do in this calculation, for example, in the effective field theory, I've done calculations like the bending angle of light around a massive object at a large distance. And in that calculation, it's a quantum calculation. You reproduce the classical results and you get quantum corrections proportional to h bar. It's interesting in the calculation that you're doing loop diagrams, so you're doing a full quantum calculation, but you end up with the classical results also appearing. And so if I were to do this, that's in the effective field theory, but if I did the same calculation in quadratic gravity, I would, when I went to the low energy and long distance, large impact parameter limit, I would get the same bending angle that I get in the effective field theory, which is the classical plus a term proportional to h bar. So if I'm defining my classical limit by doing full quantum calculations and then at the end setting h bar to 0, I get Einstein back again. The issue about degrees of freedom also is a scale dependent issue. We've learned to think of degrees of freedom
I interject
that
and
appear
ask
only at high energies.
what new you get, Ben?
What do I get?
Yeah, what new do you get other than what you already got, and you're the prime exponent of doing it, of using Einstein as a effective field theory?
Right. In what the only thing you get different from just the straight effective field theory is you have predictions from the fundamental theory of what the coefficients in the effective Lagrangian are. It's in some ways the same thing that you get if you're doing chiral perturbation theory without knowledge of QCD. You have generic coefficients. With knowledge of QCD, you have very specific coefficients at low energies. And so that's the only addition when you're down at low energies that you get out of doing any UV completion is you get predictions for what the low energy.
Let me see if I understand here. The non-local terms surely are just fixed by the Einstein theory, aren't they?
Yes, at leading order, yes.
So the only thing that you get is the coefficients of the local
terms.
higher derivative terms, but again, you already had that in using Einstein as an effective field theory. What new do you get by doing all this stuff with the Lee-Wick mechanism and the going around poles and everything? What new things do you get from that?
It isn't just an effective field. At low energy, you get very little extra. You get nothing extra. There's nothing valuable, put it that way.
But isn't that the only thing we can hope to measure?
The value of doing this type of theory is that you end up with a renormalizable theory rather than a non-renormalizable one. And it has the potential for being as UV complete as other renormalizable theories.
But you pay a huge price. You can't take the classical limit of the theory that you really get, and you can't talk about strong field limits. Cosmology is opaque to me. It's an S matrix theory, and
I guess I don't. I think it's much less of a price than you get in most any other approach. I'm not having 11 dimensions. I have regular particles. It's a very conservative UV completion compared to anything else that's around. But all UV completions have the same issue, that they all limit to the effective field theory, and
there are things we can do in the classical theory that we can't do in your theory, or at least that I don't know how to do in your theory, like talk about strong field regimes, talk about propagation. I can write down what the action, the field equations are. All of that stuff is opaque in this theory.
Well, it's not so opaque. I mean, Bob Holden might chime in, and it's basically the type of theory that he's been trying to do strong field calculations with black holes. It's admittedly, I am not showing anything here, but
Well, let me say it another way. If you do have a classical theory, why not just quantize that? Why ever even appeal to the higher derivative gravity theory?
I need the higher derivatives in the to modify the propagator to get renormalizability.
But if you had a classical theory, if you could tell me what this classical theory was, what its dynamical variables were, what the action principle was, and everything,
That's
why
why I
not
spent
just
some time on
quantize
that
that?
slide where I said that my pathway is I'm starting from the quantum theory, Lorentzian path integrals, and I'm limiting later on, after having identified the asymptotic states, I limit to the low energy theory. I'm not doing the reverse. And maybe the two approaches don't commute. Maybe starting with a classical theory and trying to start there doesn't end up in the same place. But so I have a pathway. I have a pathway that starts with a Lorentzian path integral. I identify the degrees of freedom. I do a bunch of calculations. I take the low energy limit, and I get things that look like the effective field theory.
Yeah, maybe if I make a comment. So, yeah, I think the more general question here is if, like in quantum gravity, a correspondence principle still makes sense or not. Because what Richard is saying, we should start from a classical Lagrangian, quantize it, and get our, let's say, quantize it in a consistent way and get our quantum Lagrangian. So in this way, we always know which is our classical limit. Okay, but in the case of John approach, we are not. I mean, John is not doing that, of course, because you're not really quantizing your classical Lagrangian, okay, because you're using something else. And so you don't recover, let's say, you don't have, let's say, a good classical limit in the sense that you don't have a correspondence principle that can tell you which is the proper good classical limit, okay? So I don't know, maybe as a more general question, I should also ask, quantum gravity means that we are really probing something at almost like at Planck scale. So does it make sense to speak of correspondence principle at those scale, or we cannot simply think of like a classical counterparts of our quantum theory, okay? In the same sense as we think of other quantum field theories, okay? So I don't know if...
Well, that's an excellent question, and I've wondered about that too. And in this particular context, I think the issue is what would we do with a theory of quantum gravity, a full, complete theory of quantum gravity, if we had it? And there are some things we'd like to know about, like what's the final state of a black hole? What's the final outcome of a black hole? What happens in the earliest stages of cosmology? We'd also like to know is if it's possible to build starships. You know, it's ever since the 1950s, quantum gravity theories have predicted blurring of the light cone, and that should be present. It hasn't been seen, but it should be present at some level, and we'd like to know all of those things. And these sort of S-matrix formalisms that are based on going around poles in exotic ways don't seem to me to answer those questions to the extent that they reproduce the known physics of classical gravitation, which we certainly don't want to throw away. They just give us what John Donahue told us, you know, about how to get by using Einstein theory as an effective field theory. So it seems to me that they don't answer the new kinds of questions that we'd like to know about in gravity, but perhaps the exponents of these models would like to tell me I'm wrong and explain how.
So Richard, sorry, just let me ask one quick question to you. So when you say, for instance, that you want a classical limit that give you some good classical Lagrangian, so you also want a good classical limit like beyond the scale which is defined by the ghost mass? Or you are happy with
if they claim that they're giving me a classical theory, if they claim that they're giving me a complete theory of quantum gravity, I want to know the things that you usually ask about a theory. What's the dynamical variable and what are the field equations? And one thing that we can tell is that it's certainly these variations of higher derivative gravities certainly don't agree with metric theories, because we have a complete catalog of all the local metric theories, and the local higher derivative metric theories are certainly unstable. Nobody disputes that. These people claim that they're avoiding all the instabilities and putting in things like acausality, which, by the way, the classical higher derivative gravity theories don't have. So it can't possibly be a local metric theory. What is it? It's a fair question, and it's germane to the issue about the whole reason for trying to develop a quantum theory of gravity. We'd like to know about what happens in strong field situations where we're not just doing a perturbation on Minkowski space, where we're looking at something legitimately non-perturbative. We'd like to know what happens in the center of a black hole. We'd like to know what happened in the earliest instance of the beginning of the universe, or at the end of the universe if it ends in a big crunch singularity. I'd like to know about whether or not we can build starships. I don't see that these things, these theories are answering any of those questions, but again, maybe I'm not seeing something.
They certainly are, in principle, can answer the questions. I think your focus on a classical theory is probably not is misguided in a way. To answer this, you really you want to answer it within the quantum theory, and of course it's painful and difficult to do, and we've only done some baby steps. I think singularity avoidance is an issue that these theories have potential to address.
I don't even know how to begin doing
it.
How do you,
as you well know, these calculations are difficult.
It was not very clear the last few seconds.
I don't even know how to begin doing that. Are you talking about some non-perturbative resummation? You don't have a classical action. It wouldn't be that I'm just taking that classical action and then expanding around some different background. I honestly don't even know how to.
Well, for a start, we also have Barvinsky sitting here. I've been trying to work towards that goal by exploring the Barvinsky-Vilkovisky expansion in the curvature, which is a non-local effective actions that can capture some of the quantum effects that we're describing. So I don't know, it's clearly not been done. Bob Holdham is trying to do black holes this way. I think there's work going on. It's not finished.
Alex Wickman, maybe you want to say something?
I actually have a very simple technical question, which I never understood on this quadratic gravity. So I'm very sympathetic to what Richard is saying, because at the end, gravity in its nonlinear regime is exactly the gravity which we use, right? Because Schwarzschild is very far away from Minkowski, and actually FRW, as we work with it, it's also far away from Minkowski. So we don't work in just scattering of gravitons. We actually, in most applications, don't even care about it. But the question would be, in normal general classical general relativity, the energy is, so the Hamiltonian is actually zero in the bulk on all solutions. And the energy actually resides on the boundary. This theory is also clearly general covariant, and but the equations with Gauss are different, because now we still have the same second derivatives, but I'm not sure that whether we really need there any kind of analog of York or Gibbons-Hawking term. So the question is, what is really with this energy? Because if you can emit so naively around Minkowski, there is this Gauss, but real energy, right, is maybe just zero if you don't have boundaries. For example, if the universe is closed, then the energy, total energy, is always zero, no? How then to understand this situation? It's one question. And second question kind of related. It's what's when John said this, that the heavy Gauss can decay, but heavy in the sense of effective field theory, so that basically the field should oscillate very, very quickly, okay? That's in that sense heavy. But if we now turn this question backwards and say, okay, but now we're around Minkowski, energy is conserved, then how heavy ghost could decay if there are no other particles with negative energies? Of course, it's not what John is doing, because John wants to preserve the positive energies, as far as I understood. And some, I cannot say I understood fully what one should do to establish that. But if you take just normal tree diagram, and I think this process could be probably analyzed on tree level, then I don't understand how can this ghost decay. Thanks a lot.
Well, I mean, it takes positive energy to excite it. So if you want to calculate the excitation, you smash two normal particles together, and you'll excite it at a positive energy. And then you look sometime later, and you see that it decays. I guess so it is a positive energy state that is excited by normal matter in the usual way that a resonance is. It just has some of these funny minus signs, but otherwise it behaves the same.
So basically, for you, it's a positive energy state, which kind of
it takes positive energy to excite it. Yes.
Okay. If the energy is, but then of course that breaks the quasi-classical approximation even for tree diagrams, no? Or it's a purely quantum process.
It's a yeah. You're excited. It is quantum, yes. So we have built in that it decays, and we built that in early. But if you calculated scattering resonance through it, you scatter in, scatter out, it satisfies unitarity. I had an explicit calculation that I had in earlier versions of the talk, but it took several slides, so I removed it to make the time limit. But you can see it in some of our papers. It behaves like a normal resonance in a scattering diagram.
If I could comment on Alex's question, one thing that the higher derivative people quite often do is to interchange positive energy creation operators with negative energy annihilation operators. So they use what's a non-normalizable state. They quantize with non-normalizable states to say that they have a negative norm rather than negative energy.
Yeah, but then it's not a Hilbert space, of course.
No kidding.
Can I come back in? I asked an initial question, and people have been answering it for quite a while, and I haven't had a chance to comment myself. I think the issue that John is raising is something that I've raised, and that is, I'm claiming in my papers that gravity should not be quantized canonically. And John is saying, I'm not going to quantize gravity canonically. His classical theory is whatever goes into the classical action in the path integral. But the classical limit is you construct the quantum theory, you construct the operators, and you take matrix elements of those operators in an infinite number of gravitons. And those are the classical observables. Now, in QED, when you do that, you find that that those matrix elements obey the same Maxwell equations that the quantum fields did, because the theory is renormalizable. And that's where John is heading. Now, the question that Richard's asking, I think, is really boiling down to, you must start with a classical theory and you must canonically quantize it. And that's not true. I mean, that's just not necessary for quantum theory. What you need is a consistent quantum theory, and then you find the classical theory afterwards, not before. Now, Richard's concern is, if you do take a classical Einstein theory and you quantize it, you get infinite radiative corrections. And so you have to conclude that none of your previous classical results are reliable unless you pretend that you will ignore the radiative corrections. And what John is doing, what Gerard is doing, what people like myself and all the others that John listed are doing, is trying to make sense of the radiative corrections. And until you do that, you have no valid reason to accept any classical gravity result as valid.
Well, if I could just speak to that, I'm happy to have you build the quantum theory first, but I want ultimately to have a classical theory to look at in order to answer strong field questions. And I just don't see what it's even going to look like. I don't see that it's going to be a local metric theory at all. It can't possibly be. And I'm at a loss to know how to analyze these theories. The theory that John is talking about is, as far as any sort of testable phenomenology at low energies, indistinguishable from just using the Einstein-Hilbert theory as a low energy effective field theory to try and answer the strong field questions that we'd like to know about. I just don't even know how to do it.
May I try to give a tentative answer to Richard?
Yes.
So I think perhaps the goal that one could give oneself could be to compute an effective action, which you may call that then a classical action, because in the end it's indistinguishable from a classical action. It's just far more complicated, because in general it will contain also lots of non-local terms and so on. So I think you probably agree that if you had an effective action calculated by anybody and given to you, you could presumably answer the questions that you're interested in. And now I agree with you that
Yes, certainly. But if I had it, why wouldn't I just quantize that? Why would I do all of, why would I ever appeal to higher derivatives and these exotic quantization schemes and everything? If you just gave me some non-local metric theory of gravity that that had an acceptable quantization, why would I not just start with that as my beginning?
Indeed, I think that if you are interested only in low energy physics, then what John has been doing with the effective field theory is enough, because that answers all the questions of low energy physics. But probably the goal now is to have an effective action that you can use also at the Planck scale or beyond the Planck scale. And so for that, you need something that goes beyond the effective field theory of GR. And for that,
certainly, but I'm granting that you could give me the effective action. But once I get it, why not just quantize that? Why in the end, maybe we need the latter to get there, I don't know. But in the end, why ever talk about higher derivative gravity? It's not a higher derivative gravity that we're quantizing.
But why not
classical
high derivative terms? High
the
derivative
classical
terms
limits
will
of-
be contained. The higher derivative
Well, if it's
terms will be
a
contained.
full-blown non-local theory, the non-local terms will be much more important in the end than the local higher derivative terms. You can see that even in one-loop corrections about flat space. You know, in Einstein-Hilbert, R squared and C squared are not the most dominant terms. The non-local corrections look like R log box R and C log box C.
At low energies, yes. And that's why, as I said,
Even at high energies,
is
when
enough.
box gets to be big, logarithms get big either way.
Mhm.
So I just I'm number one suspicious, as Gerard is, of all the rules, the kind of ad hoc rules. But let me not cast aspersions on people. You know, maybe it all works out right. My issue is, in the end, why not just take the classical limit of that if it exists, and it had better exist? Why don't we just quantize that, and it'll be some sort of probably metric, certainly non-local theory.
And the short answer is you get the effective non-local effective action by taking the limit of the quantized effective action. So but actually I'd rather not speak too much. I see Bob Holm and Starobinsky have their hands up, and I think they probably have insights on this.
Yeah, maybe there was Tomislav first.
Tomislav, okay, great. Hello.
Okay, hello everybody. Yeah, so I also made a comment in the chat, and I think it should be kind of clear from the structure of the propagator that it's effectively at low energies. Somehow it should be a theory which has a massless graviton and a very heavy tensorial degree of freedom with the wrong sign kinetic term. So we can write that action, and it's also massive. So what I suggested is Claudia, Deram, and collaborators, work this out, how it should look. And then, of course, on top of it, at low energies, there should be an expansion box over m squared containing containing these type of operators. And that should be a good expansion because this is very heavy particle. And of course, if you now calculate, for example, the one loop stress energy coming from this theory, you will get minus m to the 4th log m squared term, as usually, just what you usually get from bosonic degrees of freedom, but of course now with the wrong sign because everything is inverted. So you get a large.
What's the dynamical variable and what's the action?
No, the action you build by simply adding to the standard graviton, you add another massive tensor spin 2 degree of freedom with the opposite kinetic.
That's sounding like just the local higher derivative theory. And one thing we're sure is that whatever they're talking about, the classical limit of whatever they're talking about is not that theory, because that theory classically has negative energies, and no classical theory knows about negative norms. So that really isn't what the classical limit is.
I thought, for me, this looked like that, but maybe I'm wrong. Maybe John can clarify that.
It can't possibly be the classical limit because that theory would certainly have negative energies.
Of course,
and would be unstable, and it would be a low energy effect, even though the instability would be by things that you might say to be large masses. You would see at low energies that the theory was virulently unstable. So whatever is the classical limit of the theories that they're talking about, it's not that.
Okay, well, I still think it is that, but
maybe Alexei want to add something. I think you raise your hand, right? Yeah.
Okay. In some sense, I can even repeat what Richard has said. But I want to emphasize the same questions from a little bit different perspective, and I shall present an answer to Wickman's question. So once more, my statement is why I don't like ghosts. Even ghosts are bad at the classical level. Twelve speaking about quantizing integrity, and this is can be indeed. In fact, I shall repeat about with more details what Richard has said. Okay, so let us indeed consider the figure which has a tensor ghosts. Let's add the while squared tensor to the Einstein term, and let's consider small high frequency perturbations around any background. It's not important, and repeat the method how the Isaacson's energy momentum effective averaged energy momentum tensor is obtained, and you will see that indeed this small but high frequency perturbations with non-zero squared of the wild tensor that will indeed produce negative energy. So the first critical remark is that we don't see negative energy. Next trouble is that if we now consider, once more, not speaking about quantizing gravity, but returning to good old theory of particle creation in the external gravitational field, when there exists an elegant expression for the rate of particle creation obtained in my old paper with Isidovich, that it is proportional to the rate of the light particle creation is proportional to the 12 tensor squared. So the answer is that due to this effect, once more, I'm not speaking about quantization of the gravity itself. I'm speaking about creation of other particles by the external quasi-classical gravitational field. Then, as a result of this process, you will obtain a creation of particles and antiparticles, and it can be checked. I have checked it in the good case, in the case of R-squared-term, indeed, that in this case, one can check already from the quasi-classical equations that as a result of this creation of particles and antiparticles of matter, the amplitude of these oscillations, of these quasi-classical oscillations, will either grow with time. And this is, I think, it just the same instability about which either Richard spoke. So that's why. So I repeat once more. So ghosts, it's a separate question, but you might think of some trick how to write a probably speaking about vacuum state with a few number of particles. But if you really have state with a large number of ghosts, then my statement is that this figure is bad already at the classical level. Okay. Thank you.
Okay. I don't know if someone wants to comment on that.
How can I lower my hand? Okay.
Maybe Bob, you want to say something?
Yes, I guess the first comment to Richard, what does the classical version of QCD play in the role of our understanding of QCD?
Well, actually, that's an interesting question. There was a Russian physicist with whom I worked who wrote a book, the object of which was to do for QCD or do for non-abelian gauge theories what Jackson did for electrodynamics. So it can be analyzed, and I think that there are some interesting insights to be gained from it. But QCD, but in answer to your question, we understood QCD by its by the quantum field theory, which is, I think, where you're going.
That's right. And in another analog with QCD, I think what we're after in quantum gravity is the analog of perturbative QCD. We want to know how to scatter gravitons way above the Planck scale. Just in principle, we want to know how to do that. And again, that's not a classical question in any way.
Well, I'm not sure that these techniques are really going to be able to, well, first off, I don't necessarily agree that that's what we want to do. I don't think we'll ever be able to do that experiment. I think you can actually prove that that experiment isn't doable. The experiments that we can do, that we might in principle look at, is stuff having to do with effects that occurred in the early universe, it might, in the end, be possible to observe the final stages of a black hole evaporation. Those are all effects that could be looked at. And if acausality, if fundamental acausality occurs, if there is blurring of the light cone, that effect might be looked at in some future technology. And for all of those things, I don't think that this kind of a theory is the way that we would go about analyzing those things. But maybe, again, I'm not seeing something that you all see.
I would just like to understand gravity as well as we do QCD. And our part of our understanding of QCD is how to treat high energy scattering. If we could do the same for gravity, I think we have learned a lot about gravity. Even though we can never experimentally probe that region, we would understand it at the same level of understanding QCD.
Wouldn't you rather understand the things that we could look at, the quantum gravitational effects that we could actually observe, rather than something that we really can't observe?
As we know in QCD, those kinds of questions can be quite difficult to get at. But yet we still think
But taking your QCD analogy seriously and just pursuing it, the reason that we're interested in those sorts of scattering questions about QCD and also bound state questions about QCD is because that's what we can see experimentally. That's where we can make experimental contact with QCD. I am not differing from that perception of things. I would say that we just apply that same set of rules to quantum gravity. We should be interested in the things that we could see where we actually could see quantum gravitational effects.
Yes, and I think that we will be finding things like that.
Okay, well, more power to you all. For me, I can't even see how to do such a calculation unless you can tell me, what the dynamical variable is and what the equations of motion are. And by the way, they don't have to be, I don't make a distinction between quantum equations of motion and classical equations of motion. I would say that the classical equations of motion are, for a theory that obeys correspondence, are the Heisenberg operator equations of motion. But I need to know what those things are in order to answer those kinds of questions. Perhaps you all have a way of answering them without doing it. And if you do, more power to you all.
Yeah. May I make a remark? So I think it's very important. I think about the way Richard asked questions is very well posed, and also Bob, that you want to understand gravity as well as we understand today QCD. That's very important. But I don't see why you should deem some things to be fundamentally impossible, like Richard is suggesting. It's a very valid question. What happens, or how would you have to collide two gravitons, for instance, at energies beyond the Planck scale? If you have particles that contain too much energy, the answer will be simple. There will be black holes. I mean, that you can calculate even classically. If you have a small enough impact parameter for two gravitons, they will make black holes if you are way beyond the Planck scale. So I think the ultimate question will be, you want to understand all degrees of freedom of gravity. What does it mean to talk about a graviton beyond the Planck scale? You could very well say, well, that's just something that deforms the space-time metric, because that's what it certainly will. And you can then ask, but how do I phrase that in useful and complete equations? But I think perhaps the things will boil down to the question, we want to do gravity together with black holes. I mean, black holes perhaps form part of the fundamental degrees of freedom of gravity that you have to take separately in some way or other. And of course, that means that there are hundreds of questions to ask simultaneously, which require to be answered simultaneously, which of course is extremely difficult. So what we have to do is try to chop our problem into the smallest possible pieces and try to solve those. And I think that's what we're doing in this meeting. We ask questions about higher derivatives. That's not the final question that you want to ask in gravity. You shouldn't be interested in higher derivatives. You should be interested in what the hell are those fundamental degrees of freedom of gravity? But sure enough, higher derivatives will come on our path and we will have to handle them, deal with that situation. So those questions also well put. But I'm much more optimistic than some other people that we can we should be in a position to find those answer the questions, if not by using experiment, then by using theoretical analysis much more accurately than we do now. I think we are much too easy in hand waving away things. We shouldn't be doing that. We should try to see the complete picture. So in gravity, in the complete picture, to my taste, black holes fit there, and they present us as many problems as they solve. So black holes are a very vivid proof of the fact that we haven't really understood properly what the fundamental degrees of freedom are. First, get that out of the way, and then see where to go next. And if we cannot do experiments, the one experiment that we have is a standard model itself. It has over 20 freely adjustable parameters. Nobody understands how to compute those parameters, but those are 25 or so fundamental pieces of information that we should try to understand, for instance, by quantizing gravity. So there are lots of ways to try to address our problems. I would be a strong advocate of trying everything. So including string theory, ADS-CFT, try everything and see what sticks, see where you can get new information, and try to get the picture as complete as possible. And we're still on our way of doing this. We haven't lost hope. That should be impossible. I mean, there were times in the 60s that even for particle physics, we thought it was impossible to understand those strongly interacting particles. That is never going to work. Strong interactions, we have no way of handling that. A few years later, QCD came, and we were answering exactly those questions. So why should the same not happen for gravity? It's conceivable, but we just have to analyze and formulate our questions as accurately as we can. And my complaint here is that many people are too sloppy in asking questions, so they also get sloppy answers. You have to get things very precise. You shouldn't be happy if signs come out wrong, try to wipe them out of the way, but rather just try to address the question. What do we do with these wrong signs? Are we not making other mistakes somewhere else along the line? And how should we rephrase our questions such that those problematic signs don't arise? That's very difficult, but in the past that has been shown to be the correct alley to go. I still think that I witnessed that whole process of getting to the standard model, sort of firsthand. So yes, we were dealing with problems all the time. So far, the most accurate attempts to answer those questions have been the most fruitful ones. So look very carefully. How does a theory behave on a scaling? And you discover something. And we have to do that again and again for gravity as well. What happens when you approach the Planck scale? Try to be as accurate as possible. You'll have black holes at some point, virtual black holes. How do I put them into the equation? We shouldn't try to scare away from that, but we should try to attack those questions right up front and try to answer them. But what we're doing here is just that, but we should not be too afraid of asking difficult questions, but it helps a lot to chop the questions into small pieces. I would be a very strong advocate of that.
Can I ask Gerard whether or not you believe that it's possible that gravity might make sense, that the Einstein-Hilbert theory might make sense non-perturbatively?
Oh yes, there's the question of what quantum mechanics does, and I think we can make progress even there to understand what quantum mechanics is, because that's our big difficulty. We very well understand the equations of general relativity. Einstein gave us a beautiful theory that works in many ways, and we understand how it works, but the one thing we don't understand is what happens at the Planck scale. So, and the other problem is quantum mechanics is going to join the festivities. So now we have to take that into account, but we have to understand exactly how to do it. And I don't see why we should never be able to do so. I think that's just today's status of science is that, no, we haven't understood this problem, but we have been, as scientists, we have been in such situations very often in the past as well. And always the answers came from unexpected corners. Let's hope something like that happens again here. For instance, cosmology could, by just studying the stars, you say, hey, something happens that we can't understand unless we change something here or something there. And that would be the way to get to the truth.
Gerard, you mentioned the possibility of predicting standard model parameters by quantizing gravity. Do you know this calculation that Arnowit, Deser, and Misner did back in 1960, where they calculated on a classical level the self-energy, the self-mass of a point-charged gravitating particle?
I don't know exactly what they did, but yes, that's the kind of question you have to ask. And it obviously failed because otherwise everybody would be using it now.
Well, I bring it up because when you do that calculation, you get a finite result. You get the result that the classical electromagnetic self-energy is canceled by the gravitational self-energy, and the two give a finite result, which is independent of whatever bare mass you put in for the point particle.
Aren't you just talking about the Reissner-Nordstrom solution? Or?
No, not at all. I'm talking about a calculation where you take a point particle and you endow it with a mass, and you try and calculate a point charge particle, and you try and calculate its self-mass using classical general relativity and classical electrodynamics.
But what is a point particle in classical?
I'm sorry?
What is a point particle in classical?
Well, you regulate it as a spherical shell of radius epsilon, and then you do the calculation for arbitrary epsilon and take the limit as epsilon goes to 0. And what you get, of course, is that electromagnetism gives a 1 over epsilon positive divergence, but the gravitational interaction energy gives a minus 1 over epsilon divergence, and the two wind up canceling each other in the limit that epsilon goes to 0, and leaving a finite non-zero remainder. It's way too big to be the mass of the electron, but it's finite and completely independent of any finite bare mass that you put in. I bring this up because this is relevant to the issue that you raised about possibly using, well, if somebody could do that calculation, this is a classical calculation. If somebody could do that in quantum mechanics, which no one has ever been able to do, but if somebody could do that calculation quantum mechanically, it might be a way of doing what you just said, calculating one of the standard model parameters using a non-perturbative quantum gravitational effect.
Well, it could be done all sorts of ways. You can think of using the symmetries of the standard model, the symmetries of gravity, and try to introduce topological things. You know, we had this big surprise in QCD, actually, that a topological field configuration could explain the mass of one of the particles. That's the eta particle, which was much too heavy for QCD. But then when we realized that you have a topological solution called the instanton, it gave the answer. It explained to us why this particle is so much heavier than the others, where it was not supposed to be. So surprises like this come, and there's a hope that gravity should also give such surprises. What I've been briefly saying in a few microseconds in my talk was that in black holes, we get surprises like this. We get topologically non-trivial configurations of space and time. A black hole generates a topological knot in space and time in a very interesting way. And that could be another alley. You can now think of virtual black holes, which contribute to the interactions in some way that today we don't understand, but maybe in the future we will. And that could be very similar to QCD, actually, where all these things happen. So, but in gravity, probably we have to take everything together, which makes it infinitely difficult. So that we still have a long way to go, obviously. But so it's important to try to ask our questions as accurately as we can.
Maybe Alessandro also wants to add something.
So just two statements. So one is that one possibility is that you start from this classical theory with negative energy, you do whatever you like, maybe at the end you get back a classical theory with negative energy. And so that's why now we study the classical theories with negative energy. And we found that now they seem complete nonsense, excluded. But if you actually compute and study, it's less problematic than what it seems. And so if you want details, I put in the chat a link to a paper. Second statement, I take this theory with the ghost or whatever you like to call it. I compute scatterings at energy much bigger than the mass of the ghost. And there is a completely trivial effect. Whatever makes ultraviolet better, at the same time makes infrared worse. So you do a scattering around the Planck energy, the amount you get an infrared power divergence. So maybe this is what happens. You try to go above the Planck energy and you emit a huge amount of radiation that prevents you from going above the Planck energy. So you compute, for sure you get this effect, but it's difficult to quantify it because you will need to resum diagrams. This I don't do. I have not done. Okay, period.
No, but having particles going to the Planck scale, when they go way beyond that, you have to take into account the Shapiro effect of the gravitational force, which means that as soon as particles go beyond the Planck scale, you'll have to take into account non-trivial curvature of space and time itself, which of course is what gravity is about, but that makes it very, very difficult. It also gets nonlinear and very difficult to handle classically. So if the classical system is fundamentally nonlinear, quantization is going to be quite a complicated affair. So those are difficulties that we're up to.
No, but this theory, this for derivative gravity, you can study at weak coupling. And what I claim there exists a completely trivial weak coupling effect, which is just enhanced infrared radiation. So now the matrix stays flat, and still you lose a lot of energy. And maybe the answer is that you just never go above the Planck energy. Now you try to scatter, you lose energy by radiation of gravitons, and that's it.
Well, there's another way of getting the same feature, which is that as soon as you get beyond the Planck scale, the black hole will sort of take over. A particle will become a black hole. Certainly when you scatter two particles with a too small impact parameter, then also they'll make black holes. Black holes have this topological property that they change also the topology of space-time. If you know how to put that in from the beginning, we might get a consistent picture. I don't know. I don't know how to make a picture, but something like this could happen. And,
but sorry, the black hole is a non-perturbative effect that you have in Einstein gravity. In this theory, for derivative theory gravity, if the coupling is small, non-perturbative effects are suppressed. Just the standard stuff. Weak coupling, non-perturbative is small. You compute and you get cross sections which get as big as in Einstein theory from a dimensionless theory. And the interpretation is that you get the infrared enhancement instead of the ultraviolet divergence you got in Einstein theory. So let me tell you, it's just you take this theory, you compute at weak coupling. This is what comes out.
Yeah, infrared divergence, of course, means you want to understand what happens far away, but you want to understand it as accurately as you can. And then taking that into account, sometimes a problem. In quantum field theory, it's sometimes a problem that you have, if you have massless particles, that the infrared effects might blow up. And for instance, in pure young males without Prout angular Higgs mechanism, we have this difficulty. It's very difficult to phrase properly what the infrared limits are. And there's sometimes not easy to handle. But when they become perturbative, like in ordinary QED, then you can handle the situation again. So
Yes.
yeah.
So, no, in QED, QCD, one gets log enhancement infrared divergences, and we know how to deal with them. The claim is, in this theory, you get power enhanced infrared divergences. Whatever you do with trying to interpret the ghost. This is a big trivial effect that may contain a part of the answer to deeper questions. And so let me just post again another link.
We can also keep discussing this point in the second session, because there will be another talk by Savio, I think, which will be slightly related to this, right? So maybe we can just hear Anna was a comment. We can just take this last comment, and then we can maybe have 20 minutes break before the second session. Hi, Anna, please.
My question is again about this UV and IR in the series with ghosts. Is it that obvious that IR theory is not affected by the way how you treat ghosts in quadratic gravity?
So there's work by Claudia de Ram-Tolli recently, which makes the case that the causality violation isn't visible when you're in the effective field theory limit, and the argument is roughly that when wavelengths are large, you cannot. These are small effects, and they're unresolvable by large wavelength fields. So while I think it's a valid worry, I think it seems not to be a problem when you're at the low energy limit.
But can it be somehow justified?
Sorry?
Maybe can it be justified in a more formal way?
Well, I mean, they've done real calculations, so it's not just an argument, it's a calculation.
Yeah, of course, I had in mind the paper by Claudia, in which there are some such kind of effects. And other question is more about cosmology. Maybe it's a bit stupid, but my question is like, what will happen if you create somehow a ghost during early stage of the universe?
Yeah, that I don't know the answer to. I wish I did. I mean, they're all in the research program, and I think we should insist that we eventually answer them. But my goal has been to try to
answer this question.
Well, okay, Starvinsky's trying to answer.
Oh, please, Alex, if it can be in 2-3 minutes, because.
Okay, may I only make a short comment, but first to attract the attention of all participants, especially that young, to what we have from cosmology, and then I shall have also a question for future work, of course, to Professor Iskhoft. What we the first, well, of course, you may spend much time discussing what happens when we're discussing what happens with the scattering of two gravitons with Planck energies. But I would like to emphasize what we already have, that a quantum gravitational effects may show themselves and may be even crucial and observable at much lower energies first. And we have actually an object already measured with a rather good accuracy, and this is the primordial scalar perturbation spectrum. And what we know from our observation, that certainly it's not a condensate. It's intrinsically a stochastic Gaussian quantity, where one should say much more towards explaining which quantities actually Gaussian. And so indeed it's a very strong, so, and all fair theoretical predictions of this quantity using all known mechanisms. We don't pretend to predict deterministic value of perturbations. We only predict its average value of its squared. And so my question to Professor Croft, if he in his deterministic quantum mechanics, if he consider instead of condensate some, well, that we usually have a strongly squeezed state, can he go beyond this prediction that we can only predict that some quantity, namely the amplitude of a perturbation is intrinsically stochastic, but that we cannot predict its actual amplitude? It would be very interesting if he could use his deterministic approach to say more, that he can predict not only the average squared of this quantity, but the actual value of perturbations.
Okay.
Well, can you hear me? Yes. Well, you mentioned the deterministic interpretation of quantum mechanics actually simplifies the things from both ends. It simplifies quantum mechanics. It even simplifies the classical theory. So reducing quantum mechanics to something that you can put your hands on and calculate classically would be an enormous help. For instance, it would turn the standard model in a model which has only rational parameters. So you can't use real numbers anymore to describe constants of nature. No, they all become rational numbers. And that's what I got out of it now, which is clearly not enough to make it all work well enough to make real predictions. So I don't think that will work. It's much too early. But it does seem to simplify things. And so it gives us some new hope that maybe in the future we'll discover by accident or whatever theories that allow us to compute those numbers, which today are uncomputable. But as I said, science has been in this stage many, many times, and somehow we make progress, but usually not along predicted paths, but along totally new pathways that have been discovered just by asking the right questions. And so I would strongly advocate, ask the right questions and you'll find possibly interesting answers. So, but yes, deterministic versions of quantum mechanics simplify things. And so they would be a good way to go to have as one of your tools in trying to answer those questions. Whether everything I'm saying is correct, well, remains to be seen. When people will criticize it for sure. But I think there's good hope that we won't be in this state as we are today for several decades now, but that won't happen forever. I think we'll make progress, but in some unexpected way, by asking the right questions. So I've heard many right questions here, and many wrong ones, but yes, by trying to be accurate.
Okay. So yeah, I would say that maybe we can have 15 minutes break. But yeah, actually, many of the questions that were raised during this first discussion session, I think will be again discussed in the second session, because most of the talks basically will touch similar points. Okay, so if, I mean, time zone permitting, if all of you can be present also in the second discussion session, will be very nice. And for sure, we'll touch again points like regarding the corresponding principle, so which is the classical limit, and also questions about if there is any, makes sense to speak about strong gravity regime in gravity. So we will hear about these things in the second session. So yeah, let's resume in 15 minutes, I would say. Okay. And let's thank again all the speakers of the first session. Thank you very much. It was a nice discussion.